Okay. Hello, good morning. Thank you for joining us again. Let me start. Ask you if you have some questions about the last lecture, or the first lecture. Okay. So it seems that, or I can see the chat. Yes, okay, it seems that there are no questions. So, sorry, for me it's morning. That is the reason, because I said good morning, good afternoon. I'm not sure the time in the countries where you are. And okay, yesterday you have questions about the redshift. How to distinguish between the cosmological redshift to the velocity redshift, to put a name, or the special relativity redshift. And maybe that question could be clearly if the in one measure to compare distance. Okay, what I try to say is, in cosmology, we have a quantity known as the Hubble parameter, or Hubble constant, which codify the expansion of the universe. How we could have a measure of the expansion, we can use this quantity, which is given in terms of the scale factor. Yesterday, we studied this quantity. This quantity give us the size of the slide in which we are, okay? And let me put, okay, we can study the Hubble laws using this parameter. Or historically, Hubble discovered or studied the movement of the galaxies, and with an empirical plot, he developed a law, in which honor has the name, and the law is how is the distribution of the velocities according to the distance. And this quantity, the time derivative of the scale factor, rate with the scale factor itself, give this parameter that define the expansion. But the expansion give us also another quantities as the radius, and the time, and the Hubble time. The radius could be good using this product, where c is the speed of light, and this h is the inverse to this quantity. And as I mentioned yesterday, the node h node represents that we are talking about today. And for the time, we have only the inverse of this h. And for example, you can see that if we choose this c equal to 1, the Hubble time and the radius are equal, but with the proper dimension. So one quantity could help us to study the expansion is this. So in many equations in cosmology appears this factor, and we can read the factor in this form. It's important to mention that the time is the physical time. someone here asked yesterday about this quantity. This time is the physical time, the moving coordinates. This expression would be changed if we choose a different set of coordinates. For example, in this class, we're going to talk about the conformal time, and in that case, we should modify this quantity, but the physical meaning of the quantity is only in terms of this coordinate. I mean, when we talk about the expansion, or in physical terms, it's important insurance that we are working with the physical time. So I'm back to the previous discussion, and as you can read, to compare the redshift between galaxies and distinguish between the cosmological redshift and the redshift of the velocities, we can use the Hubble radius. So if we are working with a cluster of galaxies or a group of galaxies in which the distance between the objects, between the galaxies, are similar to the Hubble radius, this implies that we can compare the magnitude of the cosmological redshift with the velocity redshift. So we can take as synonymous the cosmological redshift and the velocity redshift, or the Doppler effect. So if there are many questions about that, we can discuss later or now, as you prefer. But okay, I'll define the quantities that I mentioned before with C equal to 1. We get again the expressions that I mentioned, and you can see that the Hubble time and the radius Hubble are equal. But we should have in mind that the assumption of C equal to 1. And yesterday, we study only the redshift, but today we're going to study the other magnitudes or the other quantities to get a best known of the cosmological distance or cosmological times. Now I'm going to present the angular distance. Is a quantity which help to the astronomers to work to get the distance between objects as stars. For example, I have a picture here that represents, is similar like the arc which we work in many physical classes. And in this case, we're going to consider a physical object. As I work with the redshift, I'm going to introduce this quantity using a physical object. This is not a physical process as in the redshift example, but we can consider an object with a physical length, L, and in this case I put D, but it's oriented orthogonal to our line of view, and we have the intersection with the path-like cone, which is really important because when we observe, or when the astronomers observed to some objects, they try to see, or they see the path-like cone. So in this case, we try to represent the cone, the distance, and the object is with this hero or with this sphere. And the value of the radial coordinate we can write as r, and we take the world line as the origin to the spatial coordinates, and we're going to consider an angle, this in this case, that this physical length obtains in the sky. So this is a way to represent the arc. You can realize that, for example, when you work with polar coordinates, you take an angle, take the radius, and when you're interested in compute the arc, you try to get, okay, this is the radius, this is the angle, and if I multiply this, you get the arc. In this case, you have the similar situation, but you know, or as you can see, this A, which depend on time, now appear in the expression for the arc. Why? Because you know the universe evolves with time, and the quantity which encode that feature is this A. So you can think in the similar way as you work with the polar coordinates, but now multiply by this factor A. So the angular distance usually is represented by this quantity, this L, that is the longitude, the length of the physical length of the object, and divided by the angle, as I mentioned before. We can consider again a null radial geodesic as the example for the redshift. But in this case, we're going to think that the ends are in this T today, and you have the N in L. And in this way, you have the similar equation that we have for the redshift. As you can remember, you have the element line, the S equal to minus dt squared plus a dt in the radial part, because we consider a null radial geodesic. So equal to 0, and you get this expression. As you can notice, I haven't assured about the shape of the universe. I'm working with a general K, and this general K have three options. The flat universe equal to 0, give us the flat universe. If you have equal to 1, you have the closed universe, and if you have -1, you have the hyperbole universe. So you can perform a change of variables in terms of the redshift that we got yesterday, and now the integral that you have in 25 turned into this expression. Okay, I'm only work with the left hand side. Okay, so yeah, sorry, I I see the chat, and at the end of this class, I'll send you this lecture and the 2 lectures that we're going to study in the next hour. And let me try to answer many questions in the slides. That was the reason, because I haven't sent the slides, because I want to hear the questions, and in the middle of the slides, I try to answer with references and with examples the questions that you have. Okay, so as I mentioned, I'm going to work first with the left-hand side of this equation, and I write in terms of the redshift. So the last equation turns into this, and now we can define this quantity. This psi is a quantity that depends on r. R is the Hubble radius. As you can notice, this quantity has the form of the inverse of this h, okay? In that sense, I say that this depends on the Hubble radius. And then we can define this distance, the angular distance, in terms of this quantity, okay? So you have this first equality came for this expression. And then I write the angular distance in terms of this quantity. Here, this quantity depends on the Hubble radius, and also this angular distance depends on this size that depends on the Hubble radius. Okay, and in this case, I'm working with the A naught that represents the A of today. And now we have this quantity which help to the astronomers. Okay, someone is asking in the chat. And let me show you. You have this example. You can think in an object with a physical length L. And this object is oriented orthogonal to this line, okay? And you have an angle subtended the object and the line. I define this quantity in terms of the L and the angle between the line of for the observer and the object, using this line and using the object. Okay, and now with this distance, I consider a null radial geodesic, okay? So I top the ends in T and in T node, and then between 0 and RT, okay? And this expression is a similar expression that we got for the redshift between the physical situation is the same. We consider a null radial geodesic. And I focus in the left-hand side of the equation, and I get this expression, and I perform the equation, and I write in terms of the redshift. Is there a question? Okay, it seems not. And I write in terms of h, and then this quantity, I put the name of size. I put this name, and this side depend on R, and define this angular distance, but now this angular distance is represented by this quantity. And now I rewrite the expression, and I put this expression here in this quantity that we had here, okay? So this L is A of T, R dt, and d theta. And you know that angular distance is this L divided by d theta. So I write all these things. Okay, is it clear? Okay. So this quantity helps us to define a new quantity known as particle horizon. Particle horizon has one characteristic. Is there a question? Or maybe it's the microphone of someone? Okay, no. Okay. With this quantity, we can get the causal contact, the characteristic of causal contact would be codified using this quantity. So again, we're going to consider a mobile observer at r equal to 0 and at the end in time f, okay? And the signals, they send like signals and are codified using this expression. As you can notice, this expression is the same that we use for the redshift and for the angular distance. And actually, we're going to use the same definition for this side. In this case, we try to rewrite all in terms of this distance that represents, again, this A codify the expansion of the universe, but now when we fix this time, you have a particular A. And this quantity will help us for the following, but let me say something about this. You can think that the Hubble radius, the quantity that we define here, is right in terms of A and the derivative of A. And it gives us the definition of the Hubble expansion. And if you take the inverse of this H, you get the Hubble radius. And the Hubble radius gives us some kind of horizon. Many people talk about the Hubble horizon instead of the Hubble radius, because this quantity codified the expansion, how the universe grow up. But in this case, we need a different notion of distance. This particle horizon is a distance that gives us the characteristic of the causal because, for example, with this physical situation, you can imagine that you have an observer sending the signals, but now I need to know from where this observer could send us the signals. So in that sense, now we are talking about the causal part of this context. And the spatial distance is different than the previous distance that I presented. It has a similar form, but now it is right in terms of the same quantities, the A and this side. Note that this side also has the three cases, the three shapes of the universe. And we need to ensure that this integral converge to the lower limit to say that this is a particle horizon, because this A has different forms. It's a question that you haven't do, but what is the form of this function? What could be the form for this function? The form for this A will be depend on the matter which fill the universe. For example, you know that radiation could be an option for matter in cosmology, and you will have a particular form for this function in the case that you have that component of the universe. But in a while, we left this A as a function, and this quantity is the distance that the light crosses from one observer to the other, but it's not just the particle horizon. For now, it's a distance, and when you add this term, now you get a physical distance. Why? Because you need a component to specify how the universe is changing. And now you have the notion of distance, but with this with this factor. Sorry? I didn't hear. Could you repeat? Or okay, it seemed there was not a question. Okay, so the distance is known as a particle horizon if the integral converges in the lower limit. Okay, so as I mentioned before, it's important to talk about the difference and the similarities between the Hubble radius and the particle horizon distance, because okay, I'm not sure if you had a cosmology course previously, but if you work with cosmology, as I mentioned, you can see that this A has different form for the components of to fill the universe, for example, the dust, the radiation, or the cosmological constant. So if you think you have radiation or dust, you can perform these quantities, and you can see that the order for the particle horizon and for the radius, for the Hubble radius, is similar. The order is equal in the case in which you have dust and radiation. But if now you have a cosmological constant, the quantities are totally different. So you can compute. It's a kind of homework. You can perform these quantities and tell me what you obtain for the case in you have dust or radiation. At the end, I show you how to compute the both quantities. But I show you a picture in which you have the particle horizon. You can think as a bigger size that the Hubble sphere of Hubble radius. This is only an illustrated picture. And okay, in this case, I try to show you how to perform only for the particle horizon, but without the explicit calculus. So if you think that the universe is filled for the dust, in this case, you can get from the Friedman equations that the explicit form for this A is this quantity. This capital A is only a constant, and this is the physical time. Okay, and then you can take this integral, ensurance that the integral converge, and then you have to multiply by this factor, and you're going to have this expression. And this is the particle horizon. And also you can perform the calculus to get the Hubble factor, and the Hubble factor is the time derivative of this A divided by this A. So this is the expression, but you can remember that the Hubble radius is the inverse of the Hubble factor. So you have the same order. I know the constant doesn't matter. The only thing that is important is the order in this T. And you can read that in this case, in which the component of matter is dust, you have the same expression for the particle horizon and for the Hubble radius. Now, if you consider radiation, if the universe is full for radiation, you have for the Friedman equations, you get this form for A, and the particle horizon, you perform the inverse of this quantity and you integrate over the time, you get this expression when you multiply by the factor of A. And you can also do for the Hubble radius, doing first the Hubble for the Hubble factor. But the things are changing with, we work with the cosmological constant. When we work with the cosmological constant, you have this expression for this A, where this H is right in terms of the cosmological constant. And for that case, the particle horizon is different. You get this expression in terms of this exponential, but if one want to compute the Hubble factor and then the Hubble radius, you get a completely different order, because you have, for the particle horizon, you have an exponential function, which is completely different for the radius of the Hubble constant here. So the lesson to learn is is forbidden take as synonymous a particle horizon and Hubble radius, because okay, we know that for the case in which the universe is full for dust or for radiation are equal in order, but not in the case in which we going to work with cosmological constant. And actually this course is about the early universe, and a particular epoch that we're going to study is a particular way in which the matter is cosmological constant, a kind of cosmological constant. So it's really important for us have the distinction between the particle horizon and Hubble radius. So let me end the session of the notions of the distance here. And if you have questions about this kind of notions, you can ask me, because I'm going to give a brief description of the dynamics and then try to connect with the problems in the early universe. So if you have questions, this is a good moment to do. Or if you want to ask at the end, it's also good. But okay, the dynamics of the universe is governed by the Einstein equations. The Einstein equations, you can read here that in the previous lesson, we work with the left-hand side, and in that case, we study what is the metric, what are the scalar components you can get only with the metric, but we haven't worked with the matter. So we need put at the equal level the geometrical part for the spacetimes and the matter of the spacetime. So in the left hand side, you have the metric and the other quantities which codify the geometry. And what were the requirements on the spacetime? You can remember that the homogeneity and the isotropy that we discussed yesterday. So if you have some kind of symmetries in one side of the equation, one expects that the other side of the equation has the same characteristics or the same symmetries. So the people try to represent this TAB in terms of a perfect fluid, okay? And the perfect fluid is right with this expression maybe you studied previously. And this U is the force velocity of the fluid, and rho is the density, while P is the pressure. And this is the geometrical part of the spacetime. So if you put this quantity in 14, you can read component by component the Einstein equations, and for which you can get the Friedman equation. Is a part that I want to work with that, but you can obtain, or maybe you studied previously how to get the Friedman equations. But if you try to perform in those days and you want to ask me, I can tell you how to get the Friedman equation. But basically, you put this T, replacing this part, and for example, you can take the 0 component in the 0 for G, give us the minus 1 in terms of the metric that we study in the beginning. For this expression, forgot this part, and you can replace this component and the components, for example, for the spatial coordinates, the II, using this factor, which will be contribute. You could perform in general using K without any election. And you can get for this quantity, you can read the 0 in terms of the U0. You can remember that the velocity should normalize it, and then you have that U00 equal to minus 1, and you multiply for this density, and the same for this quantity. And if you put together those equations, you will get the Friedman equations, which represents the dynamic and the physical properties of the fluid. And in a nutshell, those are the basic notions for cosmology. And now I'm going to move to talk what happened with the other kind of things. This is not a cosmology, a full cosmology course, but if you take the cosmology course after this topic, you start to study the thermal part of the universe, what happened with the Big Bang, with the hot Big Bang, and then with the nucleosynthesis Big Bang, and how to study the epochs of the universe using the thermal notion. But in this case, I'm going to focus in a particular time of the universe in which the people discovered many problems. So let me share the new slides. Do you have questions?
Feel free to unmute yourself if you do.
Okay. Okay. Now we have, what were the problems on cosmology in 1981 or before this year? The standard cosmological model have many issues or many problems. It needed to explain the conditions or the initial conditions for the hot Big Bang. Now, within this epoch, as the Planck era, and we still without that theory of quantum gravity to explain what happened in that. I don't know if that moment is a good work. Maybe it's a problem. Even talk about a moment or about a region in that epoch, but it's not clearly what happened. But now we have more knowledge about that, about what we don't know and what we know about the epoch. And the people at this time thought that the universe was dense and was hot, but they thought that in terms, for example, or in words of Bauman, this is one of the books of the bibliography, he said the people at that time should specify the initial conditions for this Big Bang. And they thought, okay, it's necessary to determine all the positions and the velocities for the all particles in a one initial time slice. We can think these slides as the slides that I draw in the first lecture. These slides, which represents only the space part, and we choose an initial time, the time for the hot Big Bang, and then at this moment, it was necessary to determine all the positions and all the velocities for the all particles in that slice. And for example, in the fluid approximation, when one considers the fluid as I show you in the Einstein equation, the analogous of this case is get the densities and the pressures as a functions of the positions for the whole fluid. But was not clear how to determine those conditions, and also the assumptions that they take was not really clear, or how to justify that kind of assumptions. And yesterday, someone asked me about the isotropy and the homogeneity. What is the assumption to use that features in the geometry of the universe? And was one of the questions that the people try to answer at this time, and also try to explain what happened with the extraordinary smoothness in the early universe. What is the reason? Because we can observe, or the people said, okay, if you observe in a local region, you can observe the distinguish between the material. If I observe to one side for the universe and then to the other and compare, you can argue, okay, but the universe looks different. Okay, but this, you should remember that this study is about the large structure of the universe. So we are concentrating in the large regions. So in that case, the universe looks extraordinarily smooth. So it's homogeneous and it's isotropic, but what is the justification, or what, not the justification, what is the reason because we observe the universe with that form? And also they address the problem of what happened with the regions that one expects don't have causal contact, and they observe that the regions have the causal contact. For example, in this case, the people, or in this book, he tried to address in the terms that there is no dynamical reason to expect causally disconnected regions, because you can observe, for example, the temperature in the CMB, and they obtain with an order up to 10 to -5 the difference between the temperature of two different regions. But how to explain that the regions that we expect without causal contact have causal contact? Let me perform. Oh, no. Sorry. Let me show you only one diagram. But first, yesterday, we wrote the metric or the line element with this form. Right? I'm going to consider the case k equal to 0. And for example, for the radial null geodesics, and you want to consider the full geometry, you need to add here the other part. But essentially, you have this difference. In this case, you have the physical time. You can add this phase, and this is the scale factor. But for example, you can redefine a new element of line in this way. And now you have this. And what is this time? This time is the conformal time. And as you can read, if you compare the two expressions, it's only a factor. We change here because now you have dt divided by ADT give us the conformal time. And conformal time allow us to draw the line, the null components in that, in lines that are to 45 degrees with respect to the observer lines. And I'm going to use this time to represent a situation. The conformal time to get the line signals using these forms. So you can think in this situation in which one observer here with this eta sub-zero that represents the conformal time of today, try to see to the past, try to observe and observe different regions. This is one for this part that is P, and the other, which is right in terms of Q. And what happened? They realized that it seems that the regions have no causal constant. There's a space between the two regions, but this is a fact that they had using the cosmological theory up to 1981, because they try to study different regions, and they didn't have reasons to think that the regions were causally connected. It seems that should be in causal connection, but they didn't, according to the cosmological model at that time. So this is only one of the big collection of problems that they attempt at that time. So this is known as the horizon problem. There are other kind of problems to encourage to the people to study or to give a new proposal, a new idea in the cosmological model, but this is one of them. And with the observation, when they study the CMB and measure the temperature, for example, in this case, the TP and TG, they realize that the temperature were equal up to the 10 to the minus 5 order. So they require that theory to explain why those regions were in causal connection in the past, but now no. And they try to give a justification to say that these regions were closely in the past, in the remote past. But then a mystery or one effect happened here that far apart one for the other. And what is this effect? What could be the physical effect that appear or that separate the two closely points and now apart one for each the other? And the people introduced the period of inflation. Something, no, as inflation. Something, I put this name in the slides, is known as inflation. And I'm going to explain. And what is the idea that we could have in mind about the inflation, a period in which the universe suffered an expansion, an accelerated expansion. So from we can think with this picture, we can think in one patch one small patch and then inflate to get this big region. And that's something that we had to incorporate to put. It's not the only physical reason that could work. If you have a better idea, could help us, because as I showed you, I'll show you at the end of the lectures, inflation still have many problems, but it's the best idea to work with the early universe and to solve the naturalness problem as the horizon problem that I show you. But let me show you mathematically how to incorporate this period in the early universe. But first of all, if you have questions, you can ask me. It's important for me, known if all is clear. Okay. Let me continue. The model, as in many areas of the physics, is described by an action. From the GR course, you could revisit that the action for the GR is the Einstein-Hilbert action. In this case, I'm going to add a scalar field known as inflation, that describes the inflation. This scalar field describes all the matter sector. And okay. What is exactly the time scale for the inflation right after the Big Bang? Okay, yes. In the literature, there are a confusion between the name Big Bang is in many references it's not clear when one starts to read some book, but then you realize that there are two kinds of Big Bang. Sometimes the people write Big Bang to talk about the Planck era, the start of the universe. For example, let me use this picture to it's not the best picture, but we can represent for this point in which we don't have a theory to explain what happened here, but we know that something in the Planck era happened here, and this is known as the Big Bang in many references. But also then after the inflation, there were a period known as Big Bang and nucleosynthesis, in which the atoms and the nucleus start to form, and the people known as Big Bang nucleosynthesis. So there are two kinds of Big Bang. So the people, when talk about the hot Big Bang, try to understand what happened with the beginning of the universe, something similar to the Planck era. And then talk about the PBN, or Big Bang nucleosynthesis, in which the nucleus start to form. But there are two Big Bangs, and you need to read carefully and try to see, okay, what is the kind of Big Bang that you mentioned here? For example, the question is really good here, because I'm working, when I talk about the hot Big Bang, I meant the beginning of the universe, what the cosmologists thought of in the initial conditions for the universe in 1980, more or less. But now, in the recent works, many people try to change the name to Big Bang to the Planck era. And for me, it's a better choice. Talk about the Planck era instead of Big Bang for this epoch and reserves the name for Big Bang nucleosynthesis for the epoch in which the nucleus start to form. I have heard the inflation is a particle. This theory treats it as such. In this case, I'm just talking about this part. In this case, the inflaton is a scalar field. Okay, the matter sector in this case is completely determined by this scalar field. There are many ways to work with the inflation. In this case, I think this is for me is the clear option to work with this expansion. And let me show you what is the role that this scalar field plays here. In this case, you have the Einstein-Hilbert action, and then you have a potential. This potential play the role of a cosmological constant, but not exactly a constant, because inflation is a period of accelerated expansion, but it's important that that epoch turns off. So, because, okay, now we know that we are in expansion, but the order of the expansion is completely different to the order of the expansion in the early universe. In this case, when I talk about the inflation and the expansion, the accelerated expansion, I'm working, it's really important, clarify this part, I'm working in the early universe. This is completely different to the expansion that now we have suffered. Actually, we don't know if what is the connection, or we don't have a final answer about what is the cause of, what is the nature of the bot expansions. We know what happened, more or less well defined in the early universe, and we try to study what happened with the expansion that nowadays we suffer, or the universe suffered, but it's different. And in this case, it's necessary have a cosmological constant that eventually turns off, because this is this potential that depends on the scalar field play the role of an effectively cosmological constant. Now, let me, in a moment, I'm going to explain what is the physical scenario of this action that we going to have on mind. But I'm back to the question that it could be a particle. Okay, I'm not sure who works with that case. I know that there are many ways to explain the inflation, but let me show you in this case with the scalar field. So we're going to work with the metric. Now I'm going to use this G to represent this part of the metric. This part is the known background. It's similar to the metric that I show you in the previous slides, and it's like the blackboard. Okay, I'm working with the conformal time, and for the expression 2, I'm going to consider a sum between the background, and then I'm going to add the perturbations. If you had attended the course of perturbation theory, could help us. And it's not exactly the same, but the idea could help in this case. And the inflaton field is expressed in terms of a background and the in the other modes of the field. Let me explain something about it. This is the background. This is the part of the metric which encode the homogeneity and the isotropy of the universe. And those kind of those things are representing the perturbations on this background. And for the case of the inflaton field, we have again this mode of the field and the other modes. We can notice that for this mode only depends on the time coordinate, but it's independent of the position, as in many scalar fields. When you work, you separate in terms of modes. The first only depends on the time, and the perturbations or the other modes of the field depends on time and depends on the position. And this zeta is the conformal time. And now let me talk about one thing. For example, when the people, I'm not sure if I put the reference of Linde. I'm going to send you the first paper of inflation. In that paper, the people try to solve the horizon problem. The horizon problem, the problem with causal connected regions, and try to solve a different kind of problems that they have at that time. But then the people realize that one of the best things that the inflation give us is that inflation give account for the birth of the seeds of the cosmic structure. So they try to introduce this period to solve problems as the horizon problem, the monopoles, and the other kinds of problems. But then when they started to study the physical process of this period, they realized that the fact that introduce a scalar field in the theory give us the explanation of the first cosmic structure. So then, okay, was really good, have an explanation for the naturalness problems, but the fact that the inflation give us a theory for the primordial structure becomes in the strong part of the model. Because now if you ask to the cosmologists about inflation, okay, if the people disagree with inflation, and ask why is the reason, because we or the people incorporated this period in the cosmological model, the answer will be because it's they're responsible to explain the structure, and now we have strong evidence about with the observations and with the theory for the correlations with the temperatures that we haven't explained before. And now I'm going to talk about only two characteristics of this period. One is the expansion. I started to talk about that. How in physical terms explain the expansion of the universe, and the mode responsible to explain the expansion of the universe is this. With the background, the G node and the phi node, we can explain the expansion of the universe. And when we focus on the perturbations of the metric and on the perturbations of the field, we're going to explain how to study the structure. And let me check the chat. I have. Okay, I can see the chat. Sorry, at the end I'm going to check. And this is the conformal time. In this case, as in many models, it needs assumptions. In this case, the inflation thought as an expansion period is characterized by the zero mode of the inflation field. I meant only for this mode. This is the mode responsible to expand the universe or to drive the universe to a state with a homogeneity and isotropy symmetries. Because the idea that many cosmologists have on mind is that they thought the universe with chaos, and they thought, okay, you don't have a really good argument to say that the universe was homogeneous and isotropy, as one of you, as someone asked me yesterday. What is the reason? Because you consider that the universe, so what is the physical reason to think that the universe is smooth, is homogeneous, has homogeneity and isotropy? The justification is this period, because if you think that something happened that expands the universe in an accelerated way, now you drive the universe in a state in which all the things without those symmetries now get the symmetries, because you dilute all possible inhomogeneities or anisotropics, you remove with expansion. So you have a different explanation for that assumption that I take yesterday. And also you have you have an argument to say that this mode is the only mode at in the beginning of this period in the inflation. We can think that this is the only mode that is turned on. The other modes, the people say that are in the Bunch-Davies vacuum. Maybe I'm going to discuss about that. I'm not sure if tomorrow, but in one of the future lessons. But now I'm going to focus in this zero mode of the inflation field. You realize that this only depends in time, not in the position. And in this case, you as there are many models of inflation, also you have many options for the potential. In this case, I'm going to represent this potential using a chaotic potential. The chaotic name is bad. It's really bad. As many names in physics, it's a bad name because it's not related with chaos in the sense of physics. It was a name that someone tried to add because they were thinking in the initial conditions, not in a chaotic, in a proper way to physics. But this is the well-known harmonic oscillator potential, and put together the form of the field, the form of the potential and the field, and we know that the only mode that is turned, this highly excited or is turned on, is the zero mode of the inflation field. So you can think, or you can get, for this action, you have two dynamical quantities. One is the metric and the other is the scalar field. So you expect that you're going to have two dynamical equations, one by the field and the other for the metric. Those equations are the Einstein equations and the Klein-Gordon equations. You can read this equation as similar to the Friedman equation that I mentioned in the last slide, and this is the Glenn-Gordon equation, and you can recognize the form as well. As good physicists, we're going to work with the harmonic oscillator, but in this case, the terms for the friction is this H. This H is the analogous of the Hubble parameter that I showed you previously, but remember that the expansion is codified in terms of the physical times. In this case, we have the conformal, but we have analogous form for this H. But in terms of the conformal time, if we want to study the expansion, we need to rewrite this in terms of the physical time. And let me show you what happened with this, or what is the idea to have in mind. Oh, the chat. Okay, it's not a question. Okay, now we made a choose for the potential. You can think this is the scalar field. This is the potential that depends on the scalar field. And we adopt a particular form for the potential. Okay, and maybe I'm not sure if this could be related with one of the questions, but you can think that the zero mode of the inflation field is not just the inflaton. It's only the zero mode of the inflation field. Remember that you have the inflaton separate between the background, the zero mode of the inflation field, which only depends on theta, plus this quantity, sorry. In this case, we only focus with this part. So, as you can notice, and sorry, I know that I mentioned many times, but only depends on time. You can think naively speaking, that this behaves like a particle. Maybe this is related with one of the questions. I'm not sure if the sense of the question is just this, but let me know. And you can think that this is, the behavior is like a particle rolled down to this potential, because you can see in this potential play the role of a cosmological constant. But it's not exactly a cosmological, it's not exactly a constant, because the aim to think this zero mode of inflation field as a particle is that we can think that this rolls down this potential and at the end reach to the minimum of the potential. So in this sense, we started with a value of a cosmological constant big, and over the time decreases up to turn off this cosmological constant. So in that sense, we're going to say that it's an effectively cosmological constant. But this is the zero mode of the inflation field. And this period is characterized using this equation, because you can read for this equation, you can think that is note that the equations are only for the zero mode of the inflation field, not for the whole field. It's completely different. If you try to get the equations for the full field, you're going to get a different equations. Those equations are only for the zero mode of the inflation field. And, oh, sorry. And in this case, you try to you're going to see that you need to consider some assumptions here. For example, we're going to think that the particle, this analogous to the particle, suffer the terminal velocity. You can remember that the terminal velocity is codified by the time derivative of phi 0 derivatives with time equal to 0. But now, if we decided working with the conformal time, now we need to rewrite these equations in terms of the conformal time. So we need to perform the assumptions in terms of the physical time to the conformal time. And with this, I'm going to end this lesson using this example to, there is a question. You have the analogous rolling down this potential up to the minimum, and then there is a question. As a mathematical analogy, see the equation is the same as the one for damped harmonic oscillator. Yes, yes, just that. So in this case, the friction of the physical reason to have in mind the damped part of the harmonic oscillator is the gravity part, because you have this term which encode the expansion, but have the components of the metric, have the components of the spacetime, and how change on time. So using this expression, you can realize that the damped part came from the gravity sector. Is the damped part for this zero mode of the inflation field that we can think as a particle. I'm not sure if the first question were in the sense that this kind of particle. In that case, we can think that the zero mode of the inflation field play the role or have the analogous behavior as a particle. But I know that there are many models in which they try to get the particle framework, but from the action, and it's a completely different theory. I'm not sure if the question were in that sense, but if the question was in this sense, the answer is this is the analogy to the particle. The friction is by the gravity. And then in this point, as you know, for a physical system, in this case, you have potential, some kind of potential energy, thinking in this analogous mode. But then this energy turns into the kinetics energy. And then at the end of the inflation, you're going to have a period in which the particle remains with oscillations in the minimum of the potential. And then it gives us a new period that we want to study here, but it's the part of the reheating. The reheating period follows for this expansion. And I'm going to end only with this equation. Tomorrow, I'm going to show you that if we take the assumption that the particle have or is suffer the terminal velocity, and we consider that this v is really bigger, really bigger, if we compare this v with the velocities of this particle, and we consider the change of the v and the change with compared with the velocity of the zero mode of the inflation field, we can get the proper equation to explain the motion over the potential and how the universe start to expand. And then we're going to do a jump to explain the structure, because there are two important features: the expansion and the account for the structure. So tomorrow I'm going to show you how this is the zero mode of the inflation field is responsible for the structure. And then I'm going to show you what happened when we try to turn on the modes, the other modes, or how to break the symmetry of the Bunch-Davies vacuum to get the other modes. Because, as I mentioned before, the part of the modes that depends on the positions are in the Bunch-Davies vacuum. To explain the expansion are not necessary work with this, because they depend on the position. They don't have the symmetries that have the zero mode of the inflation field. We need a mode in order to get the homogeneity and the isotropy of the universe. But then we need to generate the structure. And tomorrow we're going to see what happened with this part, how to get the other mode, and how to connect with the expansion. In what moment of the expansion the structure start to grow up. And please ask me questions for this part, because tomorrow, or not tomorrow, in this afternoon, I'll send you the slides. But if you have questions, I try to answer here, but also complement with material and try to add to the full content of the presentation. So I'm going to end here, and please go ahead with the questions. Okay, I have a question. I don't know if all the people have the questions in the chat. Yes, yes, yes. I'll send you the bot. Okay, I might be mistaken, but the early universe was very opaque during the inflation era, right? Okay, yes, I try to understand. How can we gather experimental data in order to test the current theories during that period. Okay, you're right. Maybe when you mention the early universe was very opaque during the inflation era, you talk about that I'm working in a previous epoch than the Big Bang nucleosynthesis epoch and the epochs in which the photons start to connect with other or interaction between nuclei. I read in many references that they use the word to explain that. But in that case, you're right. I'm working previously. I thought that the whole matter sector is characterized by this, by this scalar field, and all the matter is characterized with with the inflaton field. And then it expects that when inflation ends, leads to the reheating period, and then starts with the formation with the nucleus and the first element. But you have the ionization era. But at this point, you think that the only scalar field responsible to the matter is the inflaton, and then it's a different branch to study. It's cosmology, but a different branch to study. They try to understand how this inflaton they in the standard cosmology part in the standard particle model, but it's a different story. And then you have a second part of the question. How can we get their experimental data in order to test the current theories during that period? Okay, there are many ways to test this period. One of them is using the CMB data. Now, we have a really good evidence about the characteristics of the early universe as temperature, for example. You can measure the temperature from one side and compare it with the other and try to study. I'm going to do a spoiler, but the cosmologists try to study how this quantity has a relation with the temperature. So the fluctuations, the change in the temperature of different regions, the way in it changes, the people codifies that changes with this quantity, and then study the theory. They perform an analysis only with the theory, and it's really amazing that the results of the theory are similar when we have the data from Planck, for example. I only name one of them, and then compare the orders and are similar. So in that case, the people say, okay, inflation is a really good theory because explain the CMB, explain the kind of things that we observe with a theory. So if they work in a different way with the theory, with the observation, and then put together the theory with the data, and these are according to the expected. So in that sense, inflation works perfect. But as I will show you, there are questions that we try to understand, and we try to address even the question why or why is the reason? Because the observations match perfect with the theory. What is behind? What is the theory? We try to explore, and I try to encourage you to ask all all the features of this theory, because I'll use one part for the quantum world. In the following lessons, I try to give a quantum version of this. So in that, when when you try to put together, even I'm not working in a Planck era, but I try to work with quantum in GR, the conflict starts. So we can ask many things about it, but tomorrow I present that case. And for example, the Gether experiments, yes, you can take the Gether experiment, but further you can think in the observations, the real, in the sense that you get the observations, and then also you get the theory. So maybe it's beyond that, the Gether experiment, and you obtain that the theory and the observations match perfect. In that sense, it seems that the theory works really good in that sense. And how can we talk of large structure in the early universe? I mean, within the fluctuations in the high energy realms of measurements. Aren't fluctuations persisting out at the large scale? Okay, no. I mentioned that cosmology is a branch of the physics responsible to study the universe, the large structure of the universe. But not, you can study a particular region of the universe, but in that case, you have a particular system. It's maybe it's not compelling to the cosmology give you a theory for that system. The cosmology is a branch for the large scale structure. So in that case, you can talk about the homogeneity and the isotropy of the universe, because the idea is tough in large regions. No, if you only see a small region, you don't have that kind of features. So in that sense, I mentioned that cosmology is the branch of physics to study the large scale structure. And in a particular epoch is the early universe. So cosmology is a full branch. Now I'm going to work in the early universe, but the idea of cosmology again is to study the large scale of the universe. So I don't know if the things that I mentioned could be bad or confused, but you in that case you can think, for example, in the you mentioned how to think the fluctuations in the high energy when we perform measurements. Yes, because the people study the fluctuations in the whole sphere, in the whole regions that they could access. I know that large, or maybe you try to refer to how to codify what is large. And it's a good question, because okay, maybe if we adopt a philosophical thinking, you can say, okay, but is large with respect to us, and what could be large with respect to other kind of of notions. But in this case, I try to see the big slides of space time. In that sense, maybe I need to attend the philosophical the philosophy course of inflation. But I don't know if I answer more or less your question. Let me know. Aren't fluctuations persisting out a large scale? Yes, fluctuations, study the fluctuations. Fluctuations, I haven't seen the last part of the question. And fluctuations, mm, now I have an idea. The last session, I'm going to talk about the fluctuations, particularly the kinds of fluctuations. But fluctuations is like talk about the harmonic oscillator. It's a characteristic in the, or it's a tool for the whole physics, not only for cosmology. I'm going to apply in cosmology, but it's beyond the meaning and the way in which we work with fluctuations is beyond cosmology. So in that sense, fluctuations is a physical process, and there are many kinds of fluctuations. In this case, okay, no, maybe it's early to talk about with precision about fluctuations, but maybe in the last class, I'm going to talk about the kinds of fluctuations and what is the role that they play in cosmology. Okay, and is there a certain limit to the distance to determine when exactly we are seeing the large scale? Is there a certain limit to distance to determine? Okay. At the end, let me know if I answer your question. But um, as I show you yesterday and today, we have different notions to measure in cosmology. One of them is the Hubble radius, and the Hubble radius gives us a notion of an horizon for an event, for example. And we have a different notion of distance given by the particle horizon. The particle horizon tells us about the causal connected regions. So we can think that in a large scale patch, but also thinking the causal connected regions, for example, because many times we want to study the regions with causal connection, or many times we want to study the horizon of a process. In that case, many times we work with the Hubble horizon, but maybe for me and for the things that I read, I think the notions of large scale or to get an scale is using the Hubble radius or the particle horizon. It depends of the situation, but those measures could help us to get an intuition or a kind of limit. It's not precisely a limit, but could help us to give a notion of large scale in this context. I'm going to... Okay, I could extract the questions from the chat, and then I try to complement the slides with answers or better answers to your questions. For example, the questions that regarding the fluctuations will be incorporated in the last session, not now, but there are many questions that I could incorporate to the presentation. So, do you have more questions? Okay, for me also it's valid that you can tell me I'm not happy with your answer, and we can we can take a discussion about that. For me, it's really good when you are not agree with the question. So with the answer, I agree with the questions. So,
Well, it appears
okay.
that nobody else has questions, so let's
Oh,
thanks Professor Laurie again, and we'll see you all again tomorrow. The recording. See you tomorrow.